All right, so let's talk about PA5. This is your last programming assignment, which is good because it's due the last day of class, so no room to fit another one in. But you can finish this early if you like, right? And then take the rest of the quarter off. So this is a group project, okay? It's the one and only group project in this term. It's a group project partially because it's a really good program to break up into pieces. So you can work alone or in groups of 2 or 3. Okay, maximum group size is 3. So find a friend quickly if you want to do that before they get grabbed. And in the beginning of your main program, you need to, must to, absolutely have to have comments that tell me the full name of each person in your group, and also describes what part of the program each person worked on. Okay, I'm going to be a stickler on this. And I don't want you to say, we kind of all worked on it together. Okay, that may be true, but what I want you to do up front before you actually start writing code is get together as a group and think about what are the different pieces of this assignment. Okay, there's reading in the inventory of items, right? Coming up with a way to store that. There's writing the MaxVal function. There's writing the main function. There's doing error checking in case the inventory file is corrupt, or in case you're asked to solve the problem for a capacity of haha, right? There may be documentation if you're not going to comment this as you go. You may have somebody who goes through and adds the comments at the end, right? There's a lot of different pieces to this. And a group of 3 people, there's lots of work for each person to do. And you can vary from this once you start working on the project, but I want you to initially decide how could we partition this project into 3 or 2 pieces, depending on your group size, and make it very clear in the comments in the beginning of your main program how that assignment was broken out. Okay? And like I say, it's okay if you vary that along the way. If you decide, I was going to do this part, but I had a hard time with it, so I did this other part instead. But I want to see each person's contribution to the project. Okay? So give some thought to that up front. So important group-related notes. Start your program with comments, naming each person, what the particular tasks were. And then I want one and only one group member to submit their final project onto Canvas. Okay? If multiple members submit, I'm going to grade whichever one I come across first, which will probably be alphabetical. But I really want to avoid a situation where I grade an assignment and I spend 20 minutes working through it and I come up with a grade and then I get a note back saying, oh, that wasn't the final version. I turned in the final version, right? So make sure only one person turns it in, or if multiple people turn it in, make sure you all turn in the same version, okay? So those are the group-related aspects. And like I say, if you want to work alone, you're welcome to work alone. If you want groups up to 3 people, it will let you split out the work into smaller pieces, and that can be good. Good opportunity to work with Git. If you haven't been putting source code up on Git, this is a great excuse to sort of make that leap, because it's a really good way to collaborate, have a common place where you can all share code, and so on and so forth. All right, so what does PA5 do? So your program should be called PA5, and it operates as follows. A single command line argument, which is the capacity of your bag. PA515 says, solve my problem for a bag that holds 15 pounds. And there is a file in your current directory called knapsack.data. And that's the inventory of items that you're trying to choose from. And it's got to have the following format: weight, value, and name. So first column is weight, should be a valid integer. Second column is the value of that item. The third column is the name of the item. So the very first thing you're probably going to do, maybe after checking to make sure the capacity is a legal integer, is you're going to read this file in and store it somewhere so that you can get the weight and the value of each item. So that's a whole separate task in itself, right? That's opening a file, doing some input parsing, and so on. Think ODPs. Okay, so this is a mouse with weight 1, value 10, et cetera, et cetera. All right, after you've read in the knapsack.data file, stored it somewhere that you can use, you should call a function. This is the function I've been calling MaxVal that computes the maximum value. And this is just a very wordy rehash of what we've been talking about. MaxVal x returns 0 if x is less than or equal to 0. Otherwise, returns the maximum of each of these calculations, value of item 0 plus MaxVal of the diminished capacity, et cetera, et cetera. Okay, this is what we've been talking about today. In addition to printing the maximum possible value, you want to print out the inventory. So maximum value is 250, 3 mice, 2 pencils, 7 routers, or whatever. And you want to do this by caching the values that you compute in MaxVal. If you don't cache them, your program will probably never finish, at least on the test cases I'll use. So you really want to be caching these and running this efficiently. All right, in the very beginning of your program, I want your program to echo the contents of the knapsack file. So one of the first things you're going to do is open knapsack.data, read in each line, parse it into a weight, a value, and an item name, store it in some kind of structure. When you're done with that, go through your structure and just print that out for the user in some nice, easy-to-read tabular format. Okay, so that the person running this knows exactly what the set of items are that they're working with, and then go ahead and tell them what the maximum value is and how many of each item gets you that maximum value. All right, you're going to want to do error checking. So possible errors. Running the program without an argument is an error. Running the program with a capacity of ha-ha is an error. Running the program with a capacity of 0 or a negative, you can call that an error, or you can simply run your algorithm on it and come back and say the maximum value is 0. It's up to you. What you should not do is segfault or something like that. Okay. Other possible error conditions: corrupt knapsack.data file. First column is the weight, but instead it contains ha-ha. Or there's a line that has nothing on it at all. Or the item name is missing. Or the entire knapsack.data file is missing. Or you can't open it because it's not readable. Things like that. So you want to check for all these possible conditions. Basically, the things that will cause your program to do something wacky should not cause it to do something wacky. Okay, it should be handled by your program gracefully. The usual disclaimers about you only have to be as good as scanf. So assumptions, a maximum of 128 items in the knapsack.data file, which means you can use statically declared arrays. Okay, yay, you don't need the malloc, you don't need the free. So you can just make a weight array of 128, a value array of 128, and item name array of 128. And guess what? Your items have a maximum of 32 characters, so you can make those strings statically declared. So more no mallocs. And I'm not going to put any spaces in the item name. So that simplifies your parsing further. So if it's a new car, it'll have underscores or something instead of spaces. So you can pick it up with a %s basically. All right, and submission, include a makefile, put all the source code plus the makefile into a tar file, upload it to Canvas, same as usual. So my process will be to download your file into an empty directory, copy it in, untar it, say make, copy my knapsack.data file into that directory, and then say PA5 some number. And I'll try it for different capacities, and I should get out the correct inventory and value in each case. So questions on that so far? You can make your own items and weights. there's a sample, right? So that's not a bad way to go. But it should work for any.
What is knapsack? What is that term? How does the term relate to this?
Because it's a bag that you're like throwing things in. Like you're going hiking and you can only carry 50 pounds worth of stuff. But there's a value to your survival maybe of each item. So you want to maximize your survival? I don't know. I backpack with my Visa card, so I'm not a good one to ask. So there's a knapsack.data file. So here's PA5 sample. If you run it like this, it tells you have to specify the capacity. So we'll specify 1,000 pounds. So bag's capacity is 1,000, highest possible value is 14,275, which you get by putting in 3 cell phones and 142 laptops.
Isn't there a classic, there's kind of a classic like change problem in math that this is really similar to?
Yeah.
Counting of quarters and
Yeah, this is similar to trying to make change. Making change works with a greedy algorithm, though, if you set up your denominations correctly. Right, so when you make change, you give as many quarters as you can, and then as many dimes, and then as many nickels, and then as many pennies as you need. And that always works in most currency systems, but you can devise currency systems where that does not work.
it's one of I guess that's the reason why is because there's one value for that change, and these have 2 values associated with them. You have to balance that, isn't it? Something like that. Plus you have the capacity. There's more variables to it. Like you're not storing coins in a wallet that's a certain dimension, like you have to be able to.
Yeah, that's true. That's true. So the capacity is like the amount of change you're trying to make, but it's kind of like the weight and the value are the same if you're making change.
Also, the fact that coins, every lower value coin is a divisor at Ackermans.
That's true. Well, 10 doesn't divide 25. But there are some rules you can use to make sure that the greedy approach works. All right, so pick up those kinds of errors. I really should have tested this before I came in and demonstrated how great this error checking is, but let's try it anyway. There you go. So format error in knapsack.data, 25 cell phone, and so it says no weight value pairs were read, and it gives up. And if you don't have a knapsack.data, it just says no weight value pairs read. So I threw a sample knapsack data in /temp just for the format and stuff. Yay. So forget the car, buy 200 books. Make sense? So modularize, right? Break this into pieces. The real workhorse is the MaxVal function, but in some sense, that's one of the easiest pieces because it's a for loop and some calls to MaxVal, right? Keep track of a running maximum and you're good to go. A couple of if statements. But there's all these other details, right? So reading in the knapsack data itself, and like I say, we're doing ODPs that will exercise that. Some edge cases, details. So storing the inventory of items that give you the maximum value tends to trip people up sometimes. And you can kind of do it as an after step, but you may have to change fair chunks of your code. But if you start early on this, right, I think it's probably worth coding up a system that gives you the maximum value without the inventory. Getting that to work, that takes care of, you know, reading in the inventory file, parsing it, error checking potentially, the MaxVal function itself, the edge cases inside there, and then go back inside and make whatever changes you need to actually keep track of how you got that inventory. I think that's a reasonable approach, assuming you leave yourself enough time. And again, it's a group project, so you've got 2 weeks for this 3-person group. Does that mean you got 6 weeks for it? Kind of, in that parallel way. So there should be plenty of time to take this multiple ways. And caching your values is very straightforward, right? So, and let me see if I can break this really quickly. I already have it broken, so that's good. So I have a no DP version. So let's see. So here's my knapsack.data. So there's a capacity of 100, right? So 20 books, really likes buying books. So the no caching version, we'll sit there and chew on this for a while. And it's just struggling. I wonder if my memory use is going up. My CPU is doing something weird. My memory is slowly increasing. So that'll run for a while. So how do you do this caching? Well, if we just care about the maximum value itself, did I say what the maximum capacity was? Maximum weight of 1,024. So you don't have to worry. That should be what I mean by this is a maximum capacity of 1,024. I'll clarify that. So if the most you can have in your bag is 1,024 items, the most max values you're going to have to calculate are from 0 up to 1024. So you could make your save array something like 1025 and initialize it all to 0. Or actually initialize it to like something negative, because we know we're never going to have a capacity, a MaxVal that's negative. We could have a MaxVal that's 0. And so in the beginning of your MaxVal, I think, but I'm not positive, that initializes the entire array. But run some code and check it. We'll check it in a minute. I know it works with 0. I'm not positive it works with -1. So your MaxVal function can do the following. If save cap is bigger than or equal to 0, just return that saved value. Otherwise, find the maximum value, blah, 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 best equals blah, 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 and you're going to return best. But right before you do that, save it. Right. And now the next time that you come through here, right in the very beginning, you're going to find the capacity you're just going to return. And that'll save you from this, which is slowly chewing up my memory. I'm really curious what the CPU is doing now. So we'll spare it. So I'm curious if this actually initializes, so I'm just going to run it in GDB. Yeah, so that sets it to 1,000 -1s. Oh, no, it doesn't. You're right. It's only the first one. Oh, that's a bummer. Oh well. Gotta make a loop. It was a nice dream while it lasted. You could use memset. All right, so do a loop. But it's more fun to write a loop, right? Get one of those jobs where you're paid by how many lines of code you write. There was an old Dilbert comic about that. Yeah, exactly. Or make a for loop to compute the value of -1 and then like. All right, so any questions on PA5 so far? I imagine questions will come up as you get into this. Say what?
It's a presentation thing like last time.
Presentation.
Video line project.
Oh, no, no. Yeah, that was a GUI, so I wanted you to be able to drive it, but I'm telling you what this should look like, so I can test it. But you could put a GUI in front of it. You could use Zenity, yeah. That would be kind of gnarly. Sure, you can use anything from C. Well, you can do that, or you can just use system. And you can put any command in there and it'll execute it. But it's a little hard to get standard out and stuff back from that. So you might need to actually fork, and then you get into p-opens and things like that. But you can do it, right? Because what's your shell? It's just a big C program. So if the shell can do it, you can do it. There's other ways to do GUIs from C. OpenGL is a really old one, but it's never been a whole lot of fun to use. X11 is another option. So the whole X11 windowing system is really powerful, and it's been around forever, and it's very stable. And that's another option. But when we do Java in 223, we'll find lots of ways to write GUIs, and we'll use GUIs for lots of our programs. So that'll be fun. So did we talk about Ackermans function already? I think that was the Tuesday class. I just want to mention this because it's apropos to some of what we've been doing. So Ackermans function is a recursive function, has a very simple definition. So it takes two arguments, m and n. If the first argument is 0, it just returns n plus 1. If the second argument is 1, it returns, if the second argument is 0, it returns Ackermans of m minus 1 comma 1. And in general, it returns that third line Ackermans of m minus 1, and the second argument is Ackermans of m n minus 1. So each of these calculations gets smaller, right? To find a of mn, we're needing a of m n minus 1. But this second argument is itself a call to Ackermans function, and that can grow. And so it's a really easy function to code, right? I mean, that's the definition of it. So you could say if m equals 0, return n plus 1. If n is equal to 0 and m is bigger than 0, return a of m minus 1, 1. Otherwise, return that third thing. It's literally 3 lines of C code. But it's a frightening function to try to actually compute. So here's Ackermans of 1, 2. Right, so you just plug in the definitions, and it's the same as a of 0 and a1, 1, which is a of 0, a1, 0, et cetera, et cetera. Eventually comes down to a of 0, 3, which is just a 4. A of 4 comma 3 is all of this, right? And this just keeps going and going and going, and it keeps going bigger and bigger. And eventually you end up with an answer, which is 2 raised to the 2 to the 65,536 minus 3. And it's a crazy number of calls to the a function to get that result. And you can make a table of values of a of mn, and these numbers get so big so quickly we can't even express them with regular notation. We have to use what's called this up arrow notation, which is a shorthand for representing things like this: 2 raised to the 2 raised to the 2 n times, right? And this gets into like the theory of large numbers, and there's a whole branch of mathematics just dedicated to extremely large numbers and properties of extremely large numbers, way beyond what you can represent with scientific notation, right? Because scientific notation, if you wanted something with 1 billion zeros, it would be 10 to the billionth. That's not hard. What if you wanted something with that many zeros, right? 10 raised to the 10 to the billionth. And what if you wanted to do that whole process 1 billion times, right? And so this kind of notation lets you sort of grapple with that in a small amount of space on a piece of paper. And Ackermans function quickly gets up into these crazy values. And it's an interesting function in terms of things like theory of computation, because it is such a simple function to express and to code, but its behavior is just like crazy insane. And it's not, there's a comment they make up here, it's not necessarily clear from looking at this that this is actually even well defined, because if we're finding a of mn, well, in this case we've got an answer. In this case our first number gets smaller, and that's going to eventually bring us down to a base case. But in this third case, our first argument gets smaller, but our second one's probably going to get bigger, right? And if m and n happen to be something like 5 and 4, this term is going to evaluate to Ackermans of 5, 3, which is this crazy big number in here. And now that's your second argument. That's your value of n, and you need to evaluate Ackermans function of that. But it turns out this is guaranteed to always terminate and give you an actual number, but after considerable pain. So a lot of work has been done on this function, just kind of studying its behavior and characteristics, and it leads you into kind of a whole theory of computation and complex behavior, none of which we're going to have to get into, right? And the recursion that we're doing in here and next quarter is very well behaved. we always have this case where when we call our function recursively, it's a smaller problem than what we started with. And so we can put a pretty strict bound on the maximum number of times you're going to have to recurse to get down to a base case. But that's not how all functions work. An Ackermans function is kind of the classic model of a really badly behaved recursive function. So if you want to lose part of a weekend, spend some time playing with that. All right, well, we got 20 minutes left. So I'm going to go ahead and start talking about next week's topic because we're a little bit ahead of schedule. So don't forget about dynamic programming, right? And don't forget about trees because you're still probably finishing up your tree assignment. But our next topic is really sorting and searching, mainly sorting. And sorting is one of these classic computer science problems going back to at least the 50s, right? People have studied different ways to sort on a computer. And the basic problem is always the same. Say we have a set of numbers stored in memory, perhaps, and we want to rearrange these things in increasing or decreasing order. So we'd like to turn this into something like this. And there's lots of different ways to do this. And there's different ways in which you can evaluate how desirable an algorithm is for doing this. Now today, right, CPU time is cheap. We have a laptop with 4 or 8 cores, mostly doing nothing. And it's plugged into the wall, and if it unplugs, it's still got a rechargeable battery. And so we can run code on a laptop, or our phone if we like, or the server. And if it takes 30 seconds for that code to finish, who cares, right? It's a very different world. When I was in school and I was taking my first programming course, there were CPU limits on our accounts, right? So there was one machine that ran programs, and you typed up your program on punch cards, you handed it to an operator, and when it was your turn, the operator would load your program into the machine, and it would run, and it would print out the results. And somewhere magically in a cubicle with your initial on it, your cards would appear along with the printout of the results. And every account had a CPU limit on it, and the CPU limit was roughly 30 seconds. And that was your allotment for the entire semester. And if you used more than 30 seconds of CPU time, you were out of time and you had to go grovel and ask for more time. And so you'd run your program and it might take, quarter of a second. And it would record that and it would subtract it from your time budget and so on, right? The reason for this was there was one CPU and there were hundreds of students using it. And if you came in and you wanted to run a program that took 2 hours, right? For 2 hours, those hundreds of students couldn't do anything, right? So this was very strictly controlled. And in that kind of mindset and that kind of computing paradigm, the question of how to efficiently sort some numbers becomes really, really important. Because computers were shared resources, they were very scarce, and they might be used by an entire branch of the government, right? One machine. And if you wanted to get time on this, you had to argue a case and make a proposal and follow certain guidelines, and you'd get your 5 minutes of CPU time, right? So we don't really think about this a whole lot today because, if I need to sort numbers, I just use the Unix sort command. And it's plenty fast enough for me. But in a realm where CPU time was more precious, or if you were sorting 1 trillion numbers, right, these become important questions. And there was a time when computer memory was not readily available. So I've got 6 gig of main memory on my laptop because I spent $20 and bought an extra 2 gig. Okay, memory is cheap. Not always the case. So that display case down the hall, if you look on the middle shelf on the right side, there's a core memory in there. It's about this big. It's a bunch of little ferrite donuts threaded with wire going in 2 directions. That's a memory from an old computer, 1960s era. It's called a core memory. And I think that memory is something like 16 kilobytes. Okay, and it's like this big, and it was power hungry. So memory used to be really expensive. Magnetic tape was relatively cheap. So magnetic tape was used in place of main memory a lot of times. And when you wanted to take information and save it somewhere, instead of writing it in your memory, you would write it out on magnetic tape. And this is, you know, the old school magnetic tape you see in sci-fi movies where it sits on a spindle and it goes over to the other side and it wraps up on a reel over here. And there's some kind of read-write head here. And the tape can move, and as this spins, the tape moves in one direction or the other. Well, think about that. Suppose you have an array of 1 million numbers stored on this tape. If you're looking at this number right here and you want to look at the number immediately before or after it, you just have to move the tape a little bit. But if you want to look at the first number in your array, you got to spin this tape all the way back until this first piece of tape is sitting over here. And now if you want to look at the last number in your array, you got to spin the tape all the other way, right? And this takes time. A big 12-inch reel of tape might take it 5 or 6 minutes to spin from one end to the other. So imagine writing code with a memory system where you're only allowed to access things close to the last thing you accessed. And if you try to access element 0 and then try to access element 1 million, it's going to cost you 6 minutes of time. That's a really weird constraint, right? And it's one we don't have to think about usually with memory, although we do have to think about this with main memory because we have caching in our memory systems. And caching works because usually if we access this location in memory, we're going to access something close to it. And if you access physical memory at very different locations, you kill your performance, right? You defeat the idea of caching your memory values. So we still deal with this somewhat. So if you have a system like this and you want to sort a set of data, there's certain ways that'll work really well. There's ways that'll work faster if you can randomly access locations in your array without penalty. You may be able to do a faster sort, but it's not going to work if your numbers are stored on something like a physical tape. Or if you have so much data that you need to use locality of data in your caching system. So there's a lot of dimensions to this, and we kind of blissfully get to ignore most of those because our memories are fast and our CPU time is cheap and our caching is really good. But we're going to look at different styles of sorting information that, if we ignore those factors, still have fundamentally different behaviors, fundamentally different performance characteristics. And so we're going to look at a bubble sort, which you've probably coded multiple times, right? I think you do this in 121. We're going to look at an insertion sort. We're going to look at a selection sort. And these are all going to be fairly inefficient, basically order n squared. So 1 million times more data, 1 trillion times slower to sort. But what's 1 trillion to us? We can do 1 billion things a second. And then we're going to look at quick sort, which is a quick sort, and merge sort, which is a divide and conquer. And we'll look at something called a radix sort, which is really quirky. It's kind of reminiscent of what we did with tries. It sorts based on the individual characters in your number. So you break your number into a sequence of digits, and we sort based on each digit. And we'll look at a heap sort, which is not the same heap that you use when you say malloc, but it's a way to store information and pull it out in sorted order. And heap sorts are really cool. They're probably my favorite style of sort. And so these will be more like n log n, and these may be order 1, and heap I think is n log n. And we'll talk about a few others. And what are we going to sort? We'll mostly pick on integers, but there's nothing magic about integers. We can sort strings by using string compare and seeing if one string comes before or after another. We could sort programs by treating them like a really big, ridiculously long integer. And we can sort pretty much anything we want as long as there is a way to compare two things and decide which one comes before the other. And it doesn't even have to be a reasonable comparison. We could sort things, we could sort numbers by how many letters there are when you write out the number in English. Or we could alphabetize the English version of a number. Right? It doesn't have to be anything that makes sense. As long as for any two things that we're sorting, we can establish a relationship. One is bigger than, less than, or equal to the other. We can sort. And all the algorithms we work on, other than radix sort, will be kind of agnostic to what it is we're actually sorting. Radix sort is peculiar. So we'll spend next week talking about sorting. We'll go through these different examples. I may give you some ODPs to play with them, or we may just leave the coding details for next quarter. But we'll definitely spend some time on merge sort, because that's a nice recursive divide and conquer, and on heap sort, because that's just too much fun not to do. So that'll take us through week 9, and then week 10, I'm not sure what we're going to do. We might do some implementation of graphs as an extension of trees. So we might do some work with that, or we might do something else. Maybe we'll talk about tree balancing, who knows. We'll see where we are week 10. But anyway, the end's coming quickly, so yeah. So keep doing what you're doing, right? You're in good shape. Finish PA4 and move on to Knapsack, and we will be done before you know it. All right, I'll see you next time.